Hello, my name is Pracheth and welcome to my channel. So today we are going to see how UART communication protocol works in W78E052D microcontroller by UART. This is a microcontroller. This is a basic circuit. I've connected one LED and USB to UART module to upload the code. And this module we are connecting to the UART port RX and TX. So we don't require any additional connection. This is a shift register with LEDs so that I can show you how the mode 0 works. The crystal oscillator I am using is 11.0592 MHz along with 22 picofarad capacitors. Watch the beginner's guide video, link is in the description. But in that beginner's guide video I am using a 16 MHz crystal along with 47 picofarad capacitor. So make sure you replace that with 11.059 MHz crystal along with 22 picofarad capacitor, because using a 16 MHz crystal messes up the baud rate calculation only when we are using timer 1. But when using timer 2, we can use 16 MHz. So we'll see how to do that. First, make this circuit. And this is a basic diagram of UART in mode 1. RX is connected to TX and TX is connected to RX. So we have one serial port in this microcontroller. Nowadays a microcontroller with many serial port, because we want many modules like GSM module, GPS modules to be connected. That's why they've provided many serial ports, because we can connect only one module to one serial port, and one serial port contains RX and TX. These two lines, TX will transmit data, RX will receive data, and both can happen simultaneously. How? Using asynchronous communication. That's why it's called universal asynchronous receiver transmitter. So in mode 1, it acts as a asynchronous communication. It is a hardware-based serial communication protocol. That means internally there is a serial controller which manages the transmit registers and receive registers. That's why it's a hardware-based serial communication protocol, just as I2C or SPI. It allows half duplex synchronous communication in mode 0. So that's what we are going to see. That's why I've connected one shift register here. 74164 is the name of the IC, serial in parallel out shift register. So bits are transmitted at fixed speed determined by the baud rate. That's important when we will see the async communication. So this is the diagram for synchronous communication in mode 0. So in mode 0, it's half duplex. That means TX will carry the clock pulses just as in shift register, and RX will carry the data. So when we are transmitting the data from a microcontroller, we cannot receive at the same time because the clock pulses is busy sampling the data on the rising edge of the clock pulse, and once all the 8 bits are transmitted, and when this receives the data, then only it can transmit. Transmission and reception cannot happen at the same time in this synchronous mode. And here TX is connected to TX because the clock line is connected to the clock and data is connected to the data line. But here RX is connected to TX and TX is connected to RX in mode 1. And this is widely used rather than this one, which is in half duplex. So first let's see mode 0. So to set the mode, we use resistors. First one is SCON, which is very important. UART resistors. First one is SCON. This is an 8-bit resistor. And this is receive enable, TI and RI flag, transmit interrupt and receive interrupt. These are very important. So now we are seeing mode 0. So if you are transmitting the data and here all the 8 bits are received, so it will set the RI flag. And here all the 8 bits are transmitted, so it will set the TI flag. So TI flag, okay, it becomes 1 only when all bits are transmitted, and RI flag will set when all 8 bits are received. So TI flag will set when all 8 bits are transmitted, RI flag will set when all 8 bits are received. So this table is very important. SM0 and SM100, mode 0, synchronous, and here the baud rate is determined by crystal frequency divided by 12. When SM2 is 0, its crystal frequency divided by 12, and when SM2 is 1, its crystal frequency divided by 4. Okay, that determines the baud rate. The frame size is 8 bits because there is no start bit or stop bit. It's synchronous, so it doesn't require a start bit or stop bit. And here SM0 and SM1, 01, sets mode 1, asynchronous. And here timer 1 or timer 2 is used to set the baud rate. Number of bits is 10 bits because there are two additional bits, start bit and stop bit. So why we require a start bit and stop bit? So when start bit is set, the line is pulled low, and when the line is pulled low here at the TX side, there is a falling edge detector which synchronizes the clock pulses, and the bits are sampled at the fixed rate determined by the baud rate, and the data is recovered. So we require some indication for the clock to get in sync. That's why we require a start bit and a stop bit in async communication. But in synchronous communication, we don't require start bit or stop bit because we are sending data along with the clock pulses. So the clock pulses are sampling the data on the RX line, and it's getting stored in the register, just as in the shift register. So this is the circuit diagram for mode 0. So to set in mode 0, if to SM1 and SM0 and SM1 must be 0, 0. SM2 we will keep 0 because we want crystal frequency divided by 12. If you want the speed, greater speed, then you can keep this 1. Receive enable must be 1. Then only TX will start according to this diagram. So here you can see that RI bar and REN is connected to AND gate, then only TX will start. And these all bits remain 0. So the value is 0x10. So in our firmware, we will write scon is equal to 0x10, which will set our UART in mode 0. And this is the circuit diagram. This is the shift resistor 74164. The master reset must be connected to 5 volts. It requires 5 volts VCC and ground. A and B are shorted and connected to data line, which is nothing but RX of the microcontroller. And TX carries the clock pulses, which is connected to clock pulses, CP. And 8 LEDs are connected to 8 outputs, Q0 to Q7. So let's first output. To output the data, we require one more resistor SBuff. So when we'll write SBuff is equal to 0x01. Whenever we'll write load SBuff with the data, the transmission will be triggered and it will transmit. Okay, it will transmit that data, and this will carry the clock pulses to our shift register. So this is our shift register, and when all the 8 bits are transmitted, then TI flag will set here. Then once TI flag is set, we'll escape the while loop and clear the TI flag. TI is equal to 0. So yes, let's write this code in the kill IDE and upload the program and just see how the data is shifted when we write 0x01 and how the output looks like. So I connected an LED in common anode. You can see, so 0 will turn it on. So when we write 01, okay, so 00, this all LEDs will be on and this will be off. So let's see. So I've created a C file in Kill IDE. In case if you're new to Kill IDE and don't know how to create a hex file, then watch the beginner's guide video, link is in the description. So now let's write the code to set UART in mode 0 and transmit a single character. So first we have to include the library for the register. So we require two functions now. First is UART init. Another is to transmit the character. It will take our argument char ch. In a void main, we will call the UART init function. And transmit the character. 0x01. So that is 00000001. So we are transmitting the LSB as 1. LSB is 2 raised to 0th position. So we'll write the function now. So UART init will set the mode of the UART. So for that we have to pass to write 0x10 in the SCON. This will set UART in mode 0. REN is set and now void txchar. So in pass a 8-bit character. This is 8-bit data. Character is always 8-bit, and it will be loaded into the SBUF register. As soon as it's loaded in the SBUF register, the transmission will start. We have to wait till all 8 bits are transmitted. Until that time TI is 0. So once all 8 bits are transmitted, the TI will become 1. This condition will become false. Then you have to clear the TI flag again. So when TI will become 1, this condition will become false. So we'll exit from the while loop, and this line will be executed, which will reset TI to 0 so that it's available for the next transmission. So yes, this is the code. Here I have not put. So yes, let's build this. So 0 error, 0 warning, hex file is created. The code is uploaded. Now we'll connect this data to RX, and TX is the clock. So we'll connect clock line to TX. And you can see this is our data that we are sending. In the void main, we are sending 0000. The last bit is 1. So this is the last bit. But the first bit we are making 1 here, but here the last bit is 1. So the LED will turn on when 0 is sent. So all these are 0, but the last bit is 1. So this is Q7 actually. In the shift register, this is Q7, and this LED is Q0. So this means we know that this bit is sent first. That means the LSB is sent first in this case. So when we transmit data using this UART in mode 0, we know that the LSB is sent first by default. So you have to keep that in mind when we are transmitting data to a shift register. So yes, now let's create some pattern. Let's display some animations. So for that we have to write a delay function. For now I will turn this off. Pulling the data line to 1 will shift all ones, and which will turn off the LEDs. So now I will write a delay function using timer 0 in mode 0. So this is a short tutorial to recall the timers, how timer works. So if you know how the timer 0 works, you can skip this part. Now I'm going to explain how the timer 0 delay works. So the delay takes unsigned int t as a variable. So we'll write a delay function just as an Arduino to set a delay of 1 millisecond. So we'll declare a variable int I for the for loop. So the base delay is of 1 millisecond. So we are using timer 0 in mode 0. So the data in the T mode register will be 0x00. This is for the timer 1 and this is for timer 0. So we are setting timer 0 in mode 0, and later we will set timer 1 in mode 2 for the auto reload to set the baud rate in serial mode 1. So now we are using timer 0 in mode 0. Timer 0 in mode 0 is of 13 bits. So this will get repeated t times. So the base delay is of 1 millisecond. So now to set the delay of 1 millisecond, we have to load the th and tl values. th0, what values will this be? For that we require some calculation. TL0, we'll start the timer, and then we'll wait. We'll wait till the timer overflows, and once it overflows, once the TF flag is set, we'll clear it again. So it will wait here for exactly 1 milliseconds. So we want the overflow to happen after 1 milliseconds, and the maximum count is of 2 raised to 13. So let's see what is 2 raised to 13. It's 8192, but the count is incrementing by one instruction cycle. So one instruction cycle consists of 12 divided by the clock frequency 11.0592. So it takes 1.085 microseconds for one instruction. That means for one count to increment. But we want a delay of 1 millisecond. So 1000 microseconds is 1 millisecond. So 1000 divided by 1.085 will give us 921.6. So we want the overflow to happen after 921 counts are passed. We'll round it up to 921. So the overflow happens at 8192. So we will subtract 8192 minus 921. 8192 minus 921. That will give us 7271. So this value 7271 we have to load into the registers. But it's of 13 bit. So we'll convert this into binary. We'll copy this and go to programmer. So this is the binary conversion of 7271. So the first 5 bits from the LSB side will go into TL0. So 00111. So all the bits to the MSB side is all 0. So that gives us 7. So we will load TL0 is 0x07, and TH0 is the remaining 8 bits. So these 5 bits will go in TL0, and these 8 bits, okay, will go in TH0. So we'll copy this and then go to binary, paste it here. So it's E3 in hex. So TH0 will contain 0xE3. We'll save this. So it's in this way we have created a delay of 1 millisecond. So now we have loaded 7271, and when we start the timer by making TR0 is equal to 1, it will start a count from 7271, and when it reaches 8192, the TF flag will set. We will escape from this loop, and then TF is cleared again. So we will wait here exactly for 1 millisecond. And if we pass 2 here, it will wait for 2 milliseconds. If we pass 3, it will wait for 3 milliseconds. And in this way, we get a base delay of 1 millisecond. So whatever value we pass here, that many millisecond delay we will get. So now let's create an array to display a running LED pattern. And this is the hex data for creating running LED pattern 0x7f. So as now I've declared an array to create a running LED pattern. Now we'll run a for loop. So we have to declare a variable here, int a, for the for loop outside a is less than 8 a plus plus. So the array consists of 8 characters. It will go from 0 to 7 because 0 is this position. So after transmitting a single character in the array, we have to wait for 200 milliseconds each time. So yes, now let's build this code. So yes, now let's upload this hex file. So now I'll connect this data line to Rx. Yes, and you can see this running LED pattern is displayed. So in this way, we can use UART in mode 0 to send data to shift registers. It was interesting, right? So now let's move on to mode 1 and send data to the serial monitor. But this was also an interesting application. So yes, let's move on to mode 1. So now let us see UART in mode 1. So for mode 1, SM0 and SM1 must be 0, 1. The type is asynchronous communication. So it allows full duplex asynchronous communication. The baud rate is set by timer 1 or timer 2 overflow. So SM0 and SM1 are in SCON register. This is the SCON register. So writing 0, 1 will set to mode 1. The frame size is of 10 bits because there is a start bit and stop bit along with the 8 data bits. So this is a 10-bit frame in UART mode 1. So initially it's high, then the start bit is sent, then the 8 data bits, then the stop bit is sent. So whether we are receiving or transmitting, the structure remains the same. So start bit, then 8 data bits, then a stop bit. So let's see how the transmission takes place. So write to serial buffer starts the transmission. So serial buffer is a 8-bit register. So when we load data in the SBUF, the transmission starts. It resets as divide by 16 counter, and the output of that divide by 16 counter will give the clock pulses. So at the first rising edge, the start bit is put on the TX line. So this is TX line. On the first rising edge of the clock pulse, 0 goes. On the next rising edge, D0, which is our first LSB, first data bit, is put on the line. Suppose it's 1. So D0 is 1, it's put on the line. Then D1, D2, D3, and all the 8 data bits are put. And at last, the stop bit is sent. So after the stop bit is sent, the TI flag, this transmit interrupt, is set, and the communication stops. This is the flag which is set. So yes, the bits are transmitted in sync with divide by 16 counter, which is nothing but the baud rate. So this sampling that I showed is nothing but the baud rate. We'll see how to calculate baud rate. After 8 bits are transmitted, the stop bit is transmitted and TI is set. This is the serial buffer. When 8 bit is loaded, we'll start the transmission. When all 8 bits are transmitted, the stop bit is sent, TI flag is set. So transmission is easy, but receiving is very interesting. So the reception is enabled only when REN is set in the SCON. So this bit also needs to be set in the SCON register. Okay, so this makes this 0101, which is 5. So you have to load 0x50 in the SCON register. Then only receiving is enabled. When falling edge is detected, so normally it's high. So when start bit is sent, the RX line detects it because there is a falling edge detected. So there is a transition from 1 to 0 that is detected by this falling edge detector. Okay, then resets the divide by 16 counter, and the RX line is sampled and the bits are recovered. So the same baud rate, at the same rate, the RX line is sampled and bits are recovered. But here if the first bit is not 0, that means if the start bit is not 0, then this indicates the invalid start bit and the reception is aborted. So if a start bit is not detected, it will not take this 8 bits. But if a start bit is detected, all these 8 bits are stored in the register. At the end, stop bit is received. So when stop bit is received, stop bit goes in RB8 and data goes in SBUF. And RI is set. So after data goes in the SBUF, the received interrupt flag is set. So when all the 8 bits are received, the RI flag is set in the SCON register. This. So in this way the reception takes place, and these are the registers used. So SCON, we calculate value for it, right? 0101. This is 50. and T mode is used to set the timer mode. So we are using timer 1 in mode 2 auto reload to set the baud rate. So if you don't know how timer works, then watch the previous tutorial, link is in the description. So now we will set timer 1 in auto reload mode. So it's 1 0. So we have to send 2 0. So 0x20 we will load in T mode because we are using timer 0 in mode 0 for the delay, and timer 1 we are using in auto reload, 8-bit auto reload to set the baud rate. So in this peak-on register, if S mod is set, then it doubles the baud rate, and TH1 is the 8-bit reload value. So what happens in 8-bit auto reload is the TL register, TL1, it increments, and when it overflows, it loads the TH1 value back into TL1 and the counting starts from there. And again when it overflows, it again reloads automatically. So that is auto reload. So watch the timer tutorial, link is in the description. So you have to load TH1 with the 8-bit reload value that will determine the baud rate. So let's see how this TH1 value is calculated for the baud rate. So this is the crystal frequency 11.0592, okay, 0592, and in the denominator divide by 12 because one instruction cycle takes 12 clock cycles and the timer 1 is incremented on the instruction cycles. So the timer 1 will divide this frequency by x. So 12 into x goes in the denominator, the numerator is the crystal frequency. Then if S mod is set in the peak-on register, okay, if it's set, then we don't do divide by 2, but we will not set, we'll keep it 0. So write divide by 2 here. So into 2 goes in the denominator. Then divide by 16, which is our divide by 16 counter in the UART, and that will give us the baud rate. Okay. So let's keep our baud rate 9600. So 11.0592. What is 12 into 2? 24 into 16. 384x. 11.0592 divided by 384x is equal to 9600. So 9600 into 384 divided by 11.0592 megahertz into 10 raised to 6 will give us 1 over x. So x is equal to 11.0592 to 10 raised to 6 divided by 9600 into 384. So this will give us the value of x, and this x we will subtract it from the maximum count of TH1. So TH1 is of 8 bits, so it's 256. So 256 minus x will give us a value, suppose y, that will convert into hex, we'll load in TH1. So let's do this calculation and calculate x in our computer and then load it in TH1 and write a code to transmit a single character. So now let's write a code for UART in mode 1. So we will just transmit a single character first to test whether UART is working. First we'll include a library. Then we require these three functions: UART init, delay, and to transmit the character. Let's write the UART init function. So first we will load 0x50 in the SCON register, which will set UART in mode 1 and REN bit is enabled. Then T mod we load with 0x20 because we want timer 1 in mode 2. Then we will load TH1 with the value. Let's calculate that. So we got 11.0592 megahertz into 10 raised to 6 divided by 9600, which is our baud rate, into 384. So we got here 3, which is the value of x, and we need to subtract this from the maximum count of TL1, which is 256. So 256 minus 3 is 253. So let's convert 253 to hex. That's FD. So I have to load FD in TH1, 0xFD, and then start the timer, TR1. So this was the UART init function. And let's write for transmit. We'll take our argument char ch. SBUF is loaded with 8-bit data, and the transmission starts, and we'll wait in this while loop till all the 8 bits are transmitted. When all the 8 bits are transmitted, TI will set. It will escape from this while loop, break from this while loop, then TI will be cleared. This is a function to transmit a character. Now here when we will transmit a character, we will see it in the serial monitor. So you can use Arduino serial monitor, or you can use softwares like Putty and Docklite. So I'm using Docklite here. So now let's write a function for delay. So this is the delay function, and here you can see I'm using OR equal because I don't want this bits to clear, that's why. So when I use OR, the bits which are set, they are not cleared. They remain as it is. So 2 will remain in this position when we use OR equal, and here also we have to use OR equal. So now let's write a code to transmit a character. First we'll initialize the UART, then while 1, and here we'll write txchar A, your delay 500 milliseconds. Let's first build this code. So 0 error 0 warning. So this is Docklite. And you can see that A is getting received. We are transmitting it from the microcontroller, but on the computer it's getting received on the computer's COM port. That's why here it's RX, and A is getting printed with a delay of 500 milliseconds. Now stop the communication. Now let's write a function to transmit string. So for that we will write here void txstring, and it will take a character array. So M of I contains the characters, and I is the index. So first the 0th position character is transmitted. It means the first character in the string is transmitted, and it's checked whether it's null or not. And if the null is detected, then the transmission doesn't take place. In this way we transmit all the characters from start to the null. So we'll transmit now welcome. String is in double inverted. Let's build this. We are getting 2 warnings. So you have to write txstring. Yes, now we'll build this. So 0 error 0 warning. Now load this file. Okay. So welcome is getting printed on the serial monitor. So in this way we can also transmit a string using this function. So now let's write a function to receive. So void rxchar, and we will receive a character, and if we send A, then we'll turn on the LED, and if you send B, then we'll turn off the LED. We write a code in such a way. We declare character ch inside the function. Then we have to wait till we have received all the bits. Once we have received all the 8 bits, RI is set. Then clear RI. Then we will load our ch character with sbuff. So sbuff will receive all the 8 bits, and after receiving, we are loading it into this ch character variable, and then we will return ch. So yes, this is the function for receiving the character. So we'll declare a character variable char rch, which is the received character. So rch is equal to rxchar. Yes, this rxchar function, its data type must be char, because we are returning character data type from the function. So in this while loop, the rxchar function is called, and when a character is received, it goes into rch, and then if rch equal to, if it equals A, you have to turn on the LED. So for single line, we don't require brackets. Else if rch equal B, then we turn off the LED. So we'll declare LED. Initially, we want this LED to be off. Let's build this code. RCH is undefined, it's saying. Just because it's not in the scope. So now let's build this. There are 2 warnings. Yes, the delay is not called. So here you will give 2 functions that we wrote are not called. So give a delay of 100 milliseconds here, and we'll transmit a string when LED turns on, tx string LED on, and here transmit tx string LED off. So yes, and because we are writing 2 lines, now we require brackets. Okay. Now we'll build this. What? I'm still getting these errors. Okay. Let's upload this code. Let's clear this. Start the communication. And now we have to send A. So I will name this message LED on and write A here. Okay. And next message I have to LED off. I'll send B. Okay. So when I send A, the LED turns on. You can see that the green LED is on. Okay. And when I will send B, the LED turns off. So in this way, you can see that the LED turns on and off from my computer by sending commands over serial port. So here in the init function, we have used timer 1 in mode 2. So now let's see how to set baud rate using timer 2. Why we are using timer 2? Because then timer 0 and timer 1 remains free for the Modbus timing and also to give general delays. And also timer 2 has a wider range for frequency division because it's 16-bit. So yes, let's head on to the timer 2. So we can use timer 2 to generate baud rate in the baud rate generator mode. So the timer 2 overflow will determine the baud rate, and the baud rate generator mode is set when we make RCLK and TCLK1 in the T2 cons register. So there are total 4 modes in timer 2. The first 3 modes I've covered in timer 2 tutorial. Link is in the description. So if you're interested in knowing how the timer works, timer 2 is a 16-bit timer counter, then watch that tutorial. So now I have to set RCLK and TCLK1, and as you are not capturing, you have to set this 0. Okay, so both of these bits must be 1 and this 2 will be 0. So this will be 3, and to start the timer, you have to set TR to 1. So this will become 4. So that will make 34. So T2 con must be loaded with 34 to set the baud rate generator mode and start the timer. So just as how timer 1 in mode 2 works, which is a 8-bit auto reload. So here it is a 16-bit auto reload, and the reload value is in RCAP2H and RCAP2L. So timer 2 is of 16-bit, but the microcontroller is of 8-bit. So it has to use two registers, RCAP2L and RCAP2H. Both contains 88 bits. Okay. So the reload value is in RCAP2H and RCAP2L. So when the overflow will happen at 2 raised to 16, which is 65536, RCAP2H and RCAP2L, this value will be loaded in TH2 and TL2. And the counting will start from there. So the count which comes from the crystal frequency and goes to the timer 2, it goes to TH2 and TL2. So these two registers will increment. And when it reaches 65536, which is the overflow, then these two values, RCAP2H and RCAP2L, this will be loaded in TH2 and TL2, and the counting will start from there. So let's see what values to load in RCAP2H and RCAP2L so that we will get our desired baud rate, which is 9600. So we can derive the formula by using this block diagram. So I've changed the crystal frequency to 16 megahertz just to show you that we can also use now 16 megahertz when we are using timer 2. I can keep it 11.0592 also. Let's derive the formula. So 16 megahertz goes in the numerator divided by 2. Then the timer 2 also divides the frequency by x. So 2 into x. Then it's divided by 16 into 16 goes in the denominator. And that gives us the baud rate, which is 9600. So you have to find x. So x is equal to 16 megahertz, 16 into 10 raised to 6 divided by 9600 into 2 into 16. So this 16 will get cancelled out. So 10 raised to 6 divided by 9600 into 2 will give x. And this x we have to subtract from the maximum count, which is 2 raised to 16, 65536 minus x. And this value we will get some 4-digit hex number like FA21 for example. And these two we have to load in RCAP2H, and these two we have to load in RCAP2L. And the same value we have to load in TH and TL. So let's do this calculation in the calculator and modify the code for timer to baud rate. So I've changed this crystal oscillator to 16 megahertz, and the capacitors also have changed to 47 picofarad. So now let's modify the UART init function. This will remain as it is, scon is equal to 0x50 because we want serial in mode 1. We'll comment these lines for timer 1 in mode 2. And now we have to load rcap2h and rcap2l. So we'll calculate values for that. So the formula we got for x was 10 raised to 6 divided by 9600 into 2. So that gives us 52.08. Let's round this to 52. So x is 52. And now we have to subtract this from the maximum count, which is 65536. 65536 minus 52. And now this value 655484 we have to convert to hex. So in hex it is FFCC. FF will load in rcap2h. So rcap2h is equal to 0xFF and rcap2l is 0xCC. And the same values will load in TH2 and TL2. So TH2 is equal to 0xFF and now we will start the timer. So T2 con is equal to 0x34. This will set our timer to in baud rate generator mode because you are passing 3 here, and this 4 is to start the timer because you are making TR2 bit 1. So yes, this was the UART init function. Now let's build this code. Okay, it's rcap2h. So it's not 0 error, 0 warning. The rest of the code remains the same. We are receiving A and LED turns on. We receive B and LED turns off. So yes, now let's upload this code. Load the hex file. Stop the serial communication. So the code is uploaded. Now let's start the serial communication. Let's send A. The LED turns on. So when we send A, the LED turns on. When we send B, the LED turns off. This means that the data is getting transmitted and received. The baud rate is same 9600, and we have successfully set the baud rate using timer 2 in baud rate generator mode. So yes, this was the basic UART tutorial in which we saw how to transmit and receive character. In the coming videos, we will see how to interface UART based modules like RFID, GSM. Okay, so stay subscribed to my channel for more interesting electronics project. Thanks for watching.